Good morning, everyone. Thanks so much for joining us, either here in New Zealand or if you're listening from overseas. It's my pleasure. Well, first, I should say, sorry, my name is Brendan Bradley. I'm a professor here at the University of Canterbury, and also I'm the co-leader of Disciplinary Theme 1, Integrated Seismic Geohazards. And it's my pleasure this morning to introduce Chris Massey, who's our speaker. Chris is a principal scientist at GNS Science. And by way of short introduction, he is sort of the leader in landslide-related research in New Zealand. In particular, he had a huge impact in the Port Hills landslides after the 2010-2011 Canterbury earthquakes. In parallel with that, did a lot of work on what is the potential future landslide-related problems that we might have in places like Wellington. Not just earthquake-induced landslides, but also, of course, rainfall-induced landslides as well. And then making use of a good disaster, Chris led a large group of people looking at landslide and debris-related movement after the 2016 QuakeCoRE earthquake. And we're very fortunate now that in the passage of time, Chris and his team have done some fantastic work in that area. And now that their major project is sort of transitioning to a close, we invited Chris, and he very fortunately for us, agreed to provide us a summary of that major 5-year research program. So with that, Chris, pass it over to you. And just a reminder to everyone, if you can please have your microphones on mute. If you do have burning questions, feel free to post them in the chat, and we'll have about 15 minutes for Q&A at the end. So Chris, over to you, and thanks very much in advance.
Thanks, Brendan. I appreciate that. That's very kind. Brendan kindly asked if I would just talk about the Earthquake-Induced Landscape Dynamics program. Can you see my main screen? Is that the one? Cool. So it was started straight after the QuakeCoRE earthquake, maybe a year after we got it funded. So 2018 was probably the official start date, and it's finished. The funding's finished, but we're still mopping up some of the work. And using some of the data sets that it generated. And I'll talk about really where the work's gone and some of the key highlights. So all I'm going to do today is really just show some of the main highlights from this work. And I just want to acknowledge the various folks from around New Zealand and the world that have contributed to this work. We've also got a whole series of New Zealand and international research collaborators on the project, the program. So I just want to acknowledge all of their input, because it has been a truly team effort, and it's been a lot of fun. So what was the research question that we were really trying to tackle with this program? And it was looking at over what timescales do landscapes heal after major earthquakes. And the concept, or the original concept many years ago, and it seems silly now to even mention it now because we've moved on so far, is that that kind of morphologically, kind of we used to just take, the occurrence of landslides, X many number of landslides, divided by the time over which they occurred, and that's your mean annual rate of landslides. But we know that the rate of landsliding and other natural processes is non-linear over time. It peaks and troughs, and earthquakes are a real classic kind of example of how those processes, those landslide processes, will, after a major earthquake, your non-seismic landslides will increase their rates and then decay back to a nominal background rate. So the concept was that let's try to capture this non-linearity in the landscape of both earthquake-induced landslides and the impact the earthquakes have on the environment by cracking the rocks, by displacing the ground. And then what then happens after that with the rain and pore pressure re-establishment and the landsliding and ground deformation that we get in a post-earthquake environment. And this is something that we measured in the Port Hills. This work we published quite a few years ago now, and it tracked the slopes in the Port Hills through the Port Hills earthquake, Canterbury earthquake sequence. And so what we were looking at is, well, what would an earthquake like QuakeCoRE do, which was a much bigger and wider area affected. So I'm going to just talk very briefly about the data inventories that we've generated, the landslide types triggered by the earthquake, the controls on landslide locations, so where the landslides occurred. Then I'll talk about some of the highlights with regards to the co-seismic landslide source and debris volume. So this is looking at why the landslides occurred where they did and why they were this big. Then we'll have a look at where some of the sediment, where it was originally generated on the slopes, and then where it went to after the earthquakes. And then I'll just kind of bring a bit of a summary of some of the key kind of knowledge gains and that the program's identified, and but also some of the other areas that are ongoing where future work is clearly needed. And then if we have time right at the end, we can go and look at some of the tools that we've developed. I can give you an example of where they are. They're all on a website. You can look at them in your own leisure. But if we do have time, then we might just delve into some of these tools and have a look. So what was one of the really interesting things about the QuakeCoRE earthquake was I think officially there's 20 odd faults that ruptured to the surface, but in reality there's probably more than 30. And it was a unique event we thought it was a unique event in that this was like one of the first times such a large number of faults were ruptured at the same time during a major earthquake. But as we get more information, we now realize that this may be, in this setting, might be a normal kind of occurrence. But the landslides generated by the earthquake then went from the south all the way up to the north because of the nature of the fault rupture and the ground motions. And the area is uniquely hilly, as if any of you have been there, you'll know, very large slopes, and it's pretty difficult to get into, and not many people really live there, which was actually really quite a lucky thing when you start looking at some of the ground damage that we've got inland. So some of the data inventories then, we've got airborne LiDAR and aerial photography repeat surveys from before the earthquake, and then multiple survey epochs after the earthquake. We've got UAV and terrestrial LiDAR and RTK surveys in specific catchments. So we've got a regional view, but then a site specific, and then back out to regional. So this scale kind of approach is something that's been unique to this project, or it's not unique to this project, but it's something that this project has really had to grapple with. We've got drilling and geophysics, so again, real detailed, where we've drilled some of the landslides. We've got their slide surfaces. We've got the geophysics downhole, full waveform sonic, for example, televiewer, acoustic, all the really useful information. Mapping, sampling, lab testing. So we're looking at the materials, how they performed. Monitoring, so post-earthquake, how the slopes kind of continued to move or not, and how the debris continued to move. And then we have pre and post earthquake landslide inventories. We also have the earthquake landslide inventory. We've just published version 3, which is our final version that we're going to bother with. Version 3 is on design safe. It's the full version. It's full polygons, debris source area, landslide source area, debris trail polygons with attributes like landslide type, where we've identified what the landslide type is, and then an estimate of the volume. But we've also got historical landslide inventories as well that we've collated from across New Zealand for both earthquake events and non-earthquake, so rainfall events. And they've helped us understand the broader geomorphological context of the earthquake. What were the landslide distributions from rain events before the earthquake versus what were they after the earthquake. These are all publicly available. You can access them via our webs. The links can be accessed via our website, but they're in various locations. So, sorry, I should just say we had 9 PhD students that were linked with the program, 1 postdoc, overall 25 research scientists from all over the world. We had direct funding of around $6 million US, about, just under about 9 million New Zealand. But we also had a lot of co-funding and aligned funding. So it's kind of hard to put all that kind of value together with regards to money. And it lasted 5 years, but like I said, we're still using the data to do things that we weren't contracted to do under the Endeavour program, but the data sets that we've generated are now allowing us to explore new ideas and new areas under different research funding. So the earthquake generated more than 31,000 landslides. The image on the left, this is some work from Jones et al. The image on the left shows the density of landslides, and it shows that they're pretty much spread from the south to the north. And what's really interesting about this landslide, this earthquake, is that we've got 4 main geological units. And so that were in the area affected. And so because we have these 4 different geological units, their rock mass properties are very different and soil properties are very different. Now, although they're regional scale and there's local changes, the regional scale, they are very different. So what this allowed us to do then is look at some of the controls on why the landslides occurred where they did in these different materials, and then link that through to, well, how do those materials affect the landslides and the landslide volume? So if we just recap, then one of the most abundant landslides and some of the most abundant materials in the area are greywacke, which is Torles greywacke, sandstone, siltstones, mainly sandstone, Formsian land and seaward QuakeCoRE ranges, and it was by far generated the largest number of landslides. Most were relatively small in volume, but there were several few large, really big ones. The other type of materials were the Neogene to late Cretaceous and Paleogene sandstones, siltstones, and limestones. These were much more homogeneous than greywacke. Greywacke is highly jointed, really closely jointed, where these limestone, sandstones, and siltstones have much more persistent bedding, and so you generate these very big landslides. And so these landslides tend to be structurally controlled, and they're big, as you can see in these photographs here. So we then used all of that information to delve into detail. So we went to several of these landslides that were representative kind of members of these different groups of landslides in the different material types. And we looked at them in more detail through geophysics, through mapping, through drilling, through repeat surveys, and then lab testing and numerical modeling. So putting them all together and then try to simulate the actual landslides so that we could understand them and what their controls were. So just to put some of this into context, yeah. So the volume of debris that was generated in during Cyclone Gabriel in the one of the main valleys up north that people like James Brassington and co at Canterbury have been working on. So the main valley up in Tairafiti and Hawke's Bay that was affected by the by Cyclone Gabriel generated around, it was something like 30 million cubic meters of material, relatively shallow landslides. Like, you know, hundreds of thousands of landslides are mapped, but the total volumes are relatively small compared to one rock avalanche, which was the Hapuku rock avalanche, which is 21 million meters cubed. So earthquakes can produce some extremely large landslides, where Cyclone Gabriel generated a lot of landslides, but the majority were pretty tiny in comparison. So again, there's quite a physics-based reasons for why we have these differences. So some of the things we had to do then was look at that regional scale view of, well, what at the regional scale, what factors can we use that are quasi-physics based control on landslide occurrence? So what we did then is we compiled 3 landslide inventories. We have another 5 now. So we've got a total of 8 really high quality landslide inventories from earthquakes in New Zealand that span most of the materials that are present in New Zealand. And we remap those landslides, and we had folks like Brendan and his team generate ground motions for us. And we've used those then to generate a series of statistical models that allow us to look at the controls, what factors are controlling the landslides at that regional scale. One of the main differences in the work we did here is that we used the ground motion parameter, peak ground acceleration in this case, as the seismic forcing to represent the seismic forcing in the models, which meant that we could scale our landslide kind of forecast probabilities, or even our hindcast probabilities, using ground motion. So what I mean by that is that we could change the level of shaking, and you will have a change in the level of your landslide probability, which links all the way through to the numbers of landslides that could be generated. So these are not static models in that sense. They actually take the ground shaking as a dynamic input, and it varies the location and the magnitude of landsliding. These maps we've generated now for the whole of New Zealand using different annual exceedance probabilities and the PGAs associated with those from the new National Seismic Hazard Model, which is one of the examples I've got on the screen now. We have another 5 of these data sets now, so we're currently updating those and retraining those regional models to look at the differences in different regions and different geological materials. And we hope to update the version 2.1 with a version 3 later next year. So it's not just about the statistical controls, it's also about the physics and trying to understand why these landslides did what they did. And some of the work we've done then is we've looked at these statistical relationships, we've identified the main controls, we've come up with these conceptual models of using these relationships of how the slopes may operate. So this is some work that Corinne Singeisen completed as a PhD student at Canterbury, and she's now gone on to publish some of this work, which is great. And she came up with this concept that we have an incipient landslide stage. So this is the slope as it is now before the earthquake. The earthquake comes along, we get a permanent amount of ground displacement caused by the ground shaking. We then have more displacement and strain, and with that increased strain due to increased shaking and change in susceptibility of the materials, we transition the slope from essentially an incipient stage to a debris avalanching stage, and then it comes back to metastable, and then we have another earthquake and rainfall events, and so we're trying to capture that kind of cycle of the stress history of the slope and what's happened to that slope over its formation. And on the right is a series of numerical models where we've tested those different hypotheses using things like, well, if the slope's homogeneous and we put the same earthquake through it, how would it vary from using a discrete fracture network, where we've looked at the discontinuities within the rock mass. And the main differences here is that you change the shape and therefore the volume of the landslides. And that's important because if we're thinking about modeling these features, we want to try to get as accurate estimate of the volume as possible. And so what her work showed is that if we all rely on homogeneous rock masses and downgrade the strength using typical factors like GSI, which is the geological strength index, we're actually not capturing the true kind of shape and therefore volume of these failures, which are quite different when you include discrete fracture networks. We also looked at the fault damage zone. So this is the distance of landslides relevant or relative to where the faults ruptured to the surface, both rupturing faults during the earthquake and non-ruptured faults. And here what Colin Bloom was doing was trying to look at, well, what is that control? Is it just simply a ground motion, i.e. we get attenuation of shaking the distance from an actively rupturing fault? Or is there some other factor in there, like susceptibility of the rock mass within the zone and within the fault damage zone? And what Colin showed is that the widths of the fault damage zones did correlate with some of the larger landslides and an increase in landslide occurrence. And this cannot be simply explained by just the increased shaking caused by proximity to a rupturing fault. Because we also found in other areas where those faults that didn't rupture, we still found an increase in landslide density within those fault damage zones, suggesting that it's a complex interaction of seismic shaking and amplification caused by material impedance contrasts, which are a function of the damage of the actual rock mass within that fault zone. We also looked at the proximity to coast. This is some work that Colin also kind of published. And what we were looking at here is, why was there an increased landslide density along the coast? And we found that the coastal slopes were still responding to essentially erosion by the sea, and they were actually more oversteep than their equivalent inland slopes, indicating quite clearly that these coastal slopes, because of their steepness, they were more susceptible to landslides. And we also looked at for example, the fault damage zones overprinting on these oversteep slopes, and found again, where that combination of damage zone and oversteep slope came together, we found an increase in landslide susceptibility because of that rock mass damage. So some of the work then that myself and others and Katie Jones have been working on and this paper's just come out now, so please don't worry about reading the details. So it's just published a couple of weeks ago. So what this is based on is looking at trying to kind of essentially group the landslide distributions into the material type and the nature of landsliding, and then how we then estimate their volume. And one of the big breakthroughs for this project was that it was the first time a regionally extensive difference model was generated from a pre-earthquake digital elevation model minus a post-earthquake digital elevation model. So it allowed us to directly measure with uncertainty, of course, the volumes of the landslides that were generated and also the sediment. And so this work that Katie has put together really dives into detail of, like, well, what were the volume estimates? And she's kind of come up with these four different methods, because it's you're trying to get the same output, which is volume. So it's an ensemble approach. In some method one, you're doing direct differencing, where you just subtract one surface before the earthquake from the surface after the earthquake. But then in some cases, the debris covers those surfaces, so you can't do it. So then you have to look at different approaches. And she came up with a mean depth method and tested that. Then for the really big landslides, you need to go to a manual estimate, because it's just really hard to calculate the volumes if you don't. And so by doing all of that, she was able to put together the total volume estimate for the landslide. And by looking at some of those landslide volume distributions, we can start to look at which landslide sizes carried the majority of the volume and what was the controls on those. So what she found then was some of the bigger influences, using all of the previous work that we've talked about from the fault damage zone, numerical modeling, the regional distributions, found that obviously the interaction between the seismic shaking and the fault damage zones was where most of the large landslides occurred. Nearly all of the large landslides occurred within fault damage zones, either ruptured during this earthquake or damage zones associated with faults that didn't rupture. We also found that lithology was a very important control on landslide failure mechanism. So, and also then the volume. And so one of the big things that we found here is that if you don't take into account landslide, the geology and the failure mechanism and controls on the landslides themselves, it means that you can't really estimate their volumes with any accuracy. And what this shows on the right, on the middle plot, is the direct volume measurements of the landslides that we could actually calculate the volumes for using the difference model versus the different method of actual in situ, where we create 3D models of the landslides to calculate their volume. So you can see that there's almost like a 2 order of magnitude difference in volume for the same source area size. Yeah. And in what people tend to do is they tend to fit a power law to these relationships, and they just take the fit of the power law and assume that is the relationship between source area and volume, because you need a volume estimate to then think about how you're going to propagate that debris from the landslides down slope in post-earthquake, storms and such like. And what Katie's work showed is that if you do take that kind of scaling relationship that we all use, then if you look at the graphs here on the right-hand side plot, it shows quite clearly that you would be underestimating both the uncertainty but also the volume that you'd be generating from these landslides. And then what that allowed us to do then is it allowed us to sum the total volume from the landslides that were liberated by the earthquake, which is in the order of 240 million. Note the very large uncertainty. It's a huge uncertainty, but it's still smaller than some of the other estimates that others have generated based on previous earthquakes. We showed that the lithology has the largest influence. Most landslides are pretty small in depth and volume. There were very few examples where the failure surfaces were deep. And source areas less than 30,000 meters squared represent 99.7% of the total landslides, but only 40% of the total volume. So, and those bigger landslides occurred in certain materials. They didn't occur just, in all material types. And 12 of the largest landslides with source areas greater than 100,000 square meters represent about 40% of the total volume. So those big landslides do carry huge volumes of material when you look at it as a proportion of the total volume of landslides generated by the earthquake. And if you look at that in comparison to other earthquakes around the world, so this is QuakeCoRE in red on the left-hand side, using the ensemble method that Katie's just published. But if you look at these other, these other earthquakes, and Wenchuan's on a different scale because it's just completely different, you can see that QuakeCoRE really didn't generate a huge amount of debris compared to some of these other landslide generating earthquakes. And so the question there is now, and these are the ongoing questions that we're starting to look at, is, well, why? What's different? Is it a ground motion thing, or is it actually something more complicated with the rock mass and the nature of the topography? So where did all of that volume come from then? Most of it came from the Joel codes 2 and 3, which are the Neogene kind of sandstones. So if you think about the landslides in Greywacke, they're 72% of the landslide distribution, but only 56% of the volume. Where if you look at landslides in the Neogene materials, this is Joel code 2, then they only represent 10% of the landslides, but 36% of the total volume. So there's quite a difference in the landslide distributions and their volumes, and that's because the Neogene landslides are structurally controlled. They have this large scale structural control, and therefore you can generate these much bigger landslides. And so we can see that through these plots here, where we look at the different methods of calculating landslide volumes for the different source area contributions, and split between the Neogene landslides and the Greywacke landslides. And, if you just compare A, for example, which is the ensemble estimate that we've used in this study that Katie's published, you can see there's a massive difference between the area and volume distributions and the contributions to the total volume from Neogene landslides compared to Greywacke. So that's the landslides generated by the earthquake. We then go into the large incipient landslides with INSAR displacement. So this is where we're tracking using INSAR the post-earthquake deformation of some of these landslides. So we're taking out the tectonics now, and we've identified that we've got these really, really big landslides that continued to move after the earthquake for several years. And this work is Youngmen Cao. And we published this in 2022 with these very, very large landslides, and then we've continued to track them. And what we can see is this distribution that before the earthquake, some of them were moving, some of them were dormant. We had the co-seismic displacement caused by the earthquake, and then we had a period over several years where the displacement continued but decayed with time. And we've seen this in other areas for example, in the Port Hills, we've seen it with rockfall. So it's not just about large landslide displacement, it's also rockfall decay, although they're quite different mechanisms and processes. We've also, some work that's still ongoing is looking at the pre and post rainfall induced landslide distributions and inventories. So we've mapped these and we can see already that there's, if you look at the node density of landslides pre versus post earthquake, we can start seeing these decays over time, especially in the Hapuku. So this is the earthquake contribution, 21 landslides per kilometer squared, and you can see how this decays over time. And we've got these relationships now for multiple catchments on the coast. Inland, we haven't had the rain events to really kind of capture these differences because there's not many rain-induced landslides, because most of the rainfall is concentrated on the coast. And that had a big difference for where we could actually, kind of quantify these changes. And so we've used post-earthquake LiDAR epochs, and you can see them kind of here in the two images, where we've tried to quantify these volume changes over time. But in order to set a baseline, we remapped Cyclone Alison 1975 and the Cyclone Eta landslide distributions to get a feel for what the pre-earthquake rates were compared to the post-earthquake rates. And this work is currently in prep and in review. The other thing we looked at is landslide debris connectivity. So this is where the landslide debris is and where it goes. And we've spent quite a bit of work on doing that. And this is some more work that's in press. We've then looked at where that volume is on the slope. So you can see on this plot, most of it after the earthquake was up at the top of the hill slopes, and very little making it down into the valley heads and into the river channels. And what we can see now after nearly 7 years is only 10 to 15% of the co-seismic landslide debris has actually made it past the range front. Most of it is still sitting on those in the slopes and in the valleys up in the hills. And this is the work that John Tunnicliffe has been doing, which is some work we published last year, just mapping in a couple of catchments these sediment distributions using repeat LiDAR surveys. And this is quite amazing work because we've got these repeat LiDAR surveys through these different catchments and linking them directly to the forcing, in this case, the rain. So if we just then have a look at the summary of the research program key breakthroughs, well, some of them are the three main ones I wanted to share are that we've managed to link the earthquake ground shaking to the geology, to the geological structure, the landslide type, its mechanism, and the volume. And that's a really important linkage because the landslide volume is something that we then need to think about as we propagate that debris downstream and the hazard consequences of that. We can look at the pre and post earthquake rain-induced landslide occurrence and fluvial transport. There's still a lot of work to do in that space because these data sets take time, and that's what we're doing now. And the scale issue has been really important to look at it from regional to site specific and then back out into the regional scale to see what we can use to understand these different processes that are going on. The methodological advances, well, this is the first time regional scale digital surface model differencing has been used for an entire landslide inventory to try to quantify the volumes. But we also use these multi-scaled approaches from regional site scale to lab scale to try to characterize the mechanisms and the processes to understand why we've just got these volume differences. So this is quite different to just doing a data science approach where we're just looking at large data versus actually trying to understand the physics behind some of these. Because if you did do some of these regional scale analyses, you really don't need to understand some of those physics-based controls because your machine learning or AI models do it for you. But you really need to understand those mechanisms because you can end up with some perverse outcomes if you're not careful. Remote sensing using INSAR, and it was the first time we'd really used INSAR to find these big landslides, and now we're using them to we're using INSAR kind of much more frequently and much more extensively in our understanding of how these landscapes are moving or not. Some of the underexplored processes and data sets, well, the pre and post earthquake rain and how that links to landslide occurrence, the geology and structure and vegetation, because they are quite different. So, for example, immediately after the earthquake, 90% of the non-earthquake landslides, so the post-seismic landslides, were actually remobilization of the co-seismic landslides from that earthquake. So, for example, if you were really worried about landslide hazards in a post-earthquake environment, then you really need to focus on where the landslides occurred, because that's where you're going to get the non-earthquake landslides occurring. But then that flips in the time in the future to where you'll start getting rainfall-induced landslides occurring back where rainfall-induced landslides have historically and prehistorically occurred. Some of the other thing that's really important are the fault damage zones and the influence on ground motion, and not just for rainfall, earthquake-induced landslides, but also rainfall-induced landslides. And this is some more work that I'm personally really delving into now with some more NSF funding and some of our colleagues from overseas. So that's pretty much it in a nutshell. There's a whole load of guidelines and reports. There's web-based tools, there's inventories, databases, all kinds of things. If you go on to delve any deeper, then just go to slidenz.net or send me an email. We've got 36 international journal papers published so far and counting. There's a few still coming out. And it's a huge body of work, and the team have done a really good job, and we ticked all the boxes for MB, and so it's it's nice to have finished it, to be honest. And I think, Brendan, you said to me 7 or 8 years ago, there's only 2 times you're happy with an endeavor. One when you win it, and then the second time at the end when you've done it. And that's so true. So thank you for that bit of wisdom. Cheers.
Great. Thank you so much, Chris.